Hello, I will present a new data structure to solve the problem of polynomial evaluation and root finding of a polynomial. So more precisely, I will focus on polynomial with complex coefficients, and my problem is for a polynomial of degree d to first evaluate it on a d complex number, and second, to find all the roots of this polynomial zeta k. So here I will represent the complex number as points where the x coordinate is the real part and the y coordinate is the imaginary part. And here we can see an example of the roots of a random polynomial. So we have also to wonder about how we will represent numbers. So because we work with within the real, there is two possibilities, either working with arbitrary precision or finite precision. So here I will focus on finite precision arithmetic. More precisely, for example, a light year can be represented in matter with this number. This is arbitrary precision. And if we want finite precision, that is only keeping 4 digits, here the first 4 digits, then we have this number with the exponent here that will give an order of magnitude. Now, for the complexity, we will focus both on arithmetic complexity and bit complexity. Arithmetic complexity is a number of arithmetic operations, and bit complexity is a number of machine operations. And for example, if we multiply two numbers of size bit size m, then one multiplication will cost roughly m bit operations. Here the notation O tilde means that I neglect logarithmic factors. We will also, for the problem of root finding, we will need to have a representation for the output. Of course, we cannot represent exactly an algebraic number in the complex field, but we can do the following. We can represent the solution with an approximate solution, and with a program that will converge towards a solution with as many digits as we want. So a classical program for that is Newton. Given an initial point z, if we apply this recurrence, we know that if the initial point is close enough to the roots, we know that this recurrence will converge towards the roots of our polynomial. Another way to represent the roots of a polynomial is to use isolating disks. So isolating disk is a set of disks that are pairwise distinct and such that each disk contains exactly one and only one solution of the input polynomial. So just a small example for root finding. For example, here we have z4 minus epsilon times z minus 1 equals 0. The solution of this equation are z equal 1 and a cluster of 4 roots near 0. Here we can see that if epsilon is very small, in order to make sure that the disks don't overlap, we will need to use a very small radius. And this means that for what I call ill-conditioned polynomial, we won't be able to use only finite precision arithmetic. Another example is Minion Polynomial here, just to show that even with simple integer coefficients, here are the root of this polynomial, and we see that there are two roots here very close to each other, and we cannot represent them with finite precision. This is why in the rest of the talk I will focus on well-conditioned polynomials. So for the outline of my talk, I use here the Little Red Riding Hood metaphor. My goal is to solve those problems, so evaluation and root finding. For that, I want to use only low precision arithmetic, so this is the setting. I also want to avoid ill-conditioned polynomial. And I will introduce a new data structure called Hyperbolic Approximation. That will allow us to solve those problems in a quasi-linear time in D while using only low precision arithmetic. So first I detail a bit what is a condition number. So what the condition number is for the problem of finding the root of a polynomial. So this is the following. So I have a polynomial. I have a simple root of this polynomial, zeta. And then the condition number is simply the ratio between the perturbation of the roots that we have when we do a perturbation on the coefficients. So we do this ratio, we look what's happening when the perturbation of the coefficient goes towards 0. And we can see that this is this quantity. So if theta is in the unit disk, this is 1 over a modulo of f prime of theta. In particular, if theta is a double root, then that will be f prime of theta is 0, so that will be infinity. But we will focus on square-free polynomial, and this is the condition number of those polynomial. In the literature, we have several properties for polynomials that we know. So first, if the condition number is small, then there is a repulsion properties, that is the roots are not too close, and we can enclose them with large isolating disk. We know also that if the coefficients are random, that is coefficients are centered, follow a Gaussian center at 0, then with high probability the condition number will be small, and also with high probability the root will be far apart. So this is some properties that also motivate the fact that we are interested in well-conditioned polynomial. And now for the state of the art. So for evaluating a polynomial on d points, the most simple way of doing it is to evaluate it at each point independently. So for that we can use a classical evaluation scheme such as Horner. This costs d arithmetic operation. If we work with precision m, that means that it will cost dm bit operation. And we do it d times, so we have d square m bit operation. We can do better. Since 1972, there is an algorithm that can evaluate a polynomial on d point using only d arithmetic operation. However, this requires to use precision at least d, because it introduces integers of size of bit size d, and thus we still have d square operation, bit operation, to do this multipoint evaluation. There have been some improvements in the case of low degree using a piecewise polynomial approximation, and we have this complexity, which is not yet linear in d, but better, and our approach will follow this idea of using piecewise polynomial approximation. And of course, there is a very classical algorithm called FFT, fast Fourier transform, and using that, you can actually evaluate a polynomial on the unit roots of unity in only d times m bit operation. And you can also do interpolation, that is, if you know the evaluation of polynomial on those roots, then you will have recover the coefficient also in times d times m. Now for root finding, there is lots of methods. One of the most famous one is Newton approach, so it's an iterative approach I mentioned earlier. There is a nice paper here that gives some criterion to choose the initial points for your Newton method, such that you can find all the roots of your polynomial. There is also a variant, Abert-Ehrlich, that is used in MP-solves, and that is very efficient in practice. Even so, you still have a quadratic number of bit operation, at least, for when you use this method. Another approach from a complexity point of view that is optimal is approximate factorization. This has been introduced by Schönagge and improved by Victor Pan in 2002. It uses only d arithmetic operation, but still d square bit operation if you want to use it to find all the complex root of a polynomial. Finally, there are other methods such as subdivision approaches, Weierstrass, which is a Newton on a vector of roots. Also, you can reduce the problem to eigenvalue computation of a specific matrix called the companion matrix associated to your polynomial, and so on. Method also of interest, a bit more naive, but is a piecewise linear approximation. So here I just showing the real case. So if you do a piecewise linear approximation of your polynomial, you can then just solve for each linear part and return the roots that you find. Of course, sometimes it's precise, but sometimes it's less precise, or maybe sometimes you also miss some solutions. But still, in practice, it gives you a good first idea. And this leads to what we will use, which is also a piecewise approximation, piecewise polynomial approximation, which is the hyperbolic approximation. So the hyperbolic approximation, what it is, so this is, here I focus on the unit disk. And the hyperbolic approximation is first a set of disks that cover the unit disks. And this is a predefined set of disks that depends only on the degree of my polynomial and m, the precision that I want to reach for the approximation. One of the properties is that the radius of those disks gets exponentially smaller when we go toward the unit circle. And the center and the radius are given by this explicit formula here. And also for each disk, we associate a polynomial of degree m. And the polynomial is simply the following. So G is a linear transformation of the polynomial f with this formula where gamma is the center of the disk and rho the radius. And we develop this formula and we truncate it to keep only the first m coefficients. So in the end, we have a set of disks, which is roughly a set of d over m disk up to logarithmic factors. And for each disk, we have polynomial of degree m. And the main property is that if I look at the polynomial g, actually I didn't lose too much. So that is, if I look at the difference between the original polynomial and g, and I look at the norm, it is smaller than 2 power minus m times the norm of f. So that's the main property that we will use to have a good approximate evaluation and also to have a fast root finding. Now what we can wonder is how to compute this hyperbolic approximation in a quasi-linear time. And this is how we do it. So I just focus on the disk on the outer ring here. And I want to compute the polynomial associated to each of these disks. And the idea is that I will use evaluation and interpolation. So here, if I evaluate my original polynomial f at each of these points, then I can use FFT to recover the coefficient of g on each of those disks. And now the main complexity is how to evaluate my polynomial in a quasi-linear time. And this is how we do it. The idea is to compute them like that. So I first compute the evaluation of f on those red points. And this is actually just an FFT, so I can do it in a quasi-linear time. Then I focus on the second points here on each circle. And here I have almost FFT. I just need to scale the coefficients to get back to FFT. So this is the scaling part. And then I can do a FFT. And I do that again for the third, the fourth, fifth, and so on. And finally, I have computed I have evaluated my polynomial on all the points. And from a complexity point of view, scaling the coefficients, I will do that m times. So this is the loop here. And each time I scale, it costs d arithmetic operation, that is d times m bit operation. And for the FFT, I have only d over m points, so that cost me d bit operation, and I do that m times, so overall we have d times m squared. Now for the scaling, we can actually amortize, and instead of scaling the coefficient independently at each iteration of the loop, we can amortize that and have only d bit operation amortized, which is overall d times m. Okay, and then for the multipoint evaluation, so how does it work? Now that we can compute this hyperbolic approximation, so we compute it first, that is d times m operation. And I have my d points. What I'm doing is that for each disk, I query which points fall into this disk, and I evaluate g on those points. Because g has a very low degree, m, so this will be a fast evaluation. And we do that for each disk, and finally, what we can see is that we have d times m for the complexity of evaluating f on all the d points. For root finding, well, we do the same. We start with a hyperbolic approximation. Here, we don't have m given as input, because here what we want is to find isolating disk. So what we do is that we start with m equal 1, and we solve each polynomial on each disk. And we compute the enclosing disks, and finally we check if all the disks are pairwise distinct. If not, we start again with a higher d, we double it, higher m, we double it, so 2, and so on, until we find a m such that all the disks are pairwise distinct. Finally, the complexity will be dm bit operations. And what we can prove, if we analyze it properly, is that m is roughly logarithmic in the condition number. That is, for m that is roughly the logarithm of a condition number times the number of f, we are sure that the algorithm will terminate and that all the disks will be pairwise distinct. Finally, I implemented this algorithm for root finding, and here you can see the benchmark. So these are the degree of random polynomials, and we can see that for high degree, like 25,000, this new algorithm and implementation called HCRoot is roughly 10 times faster than MP-solved. That is the state-of-the-art implementation for root finding. You can also see that the code for the prototype here in Python is actually very small. So this is the full code, and it only depends on NumPy. And finally, this results on the complexity of root finding actually also gives results on the distribution of the roots for well-conditioned polynomial. What it means is that if the condition number is a constant, it means that in each disk the number of roots is constant. In particular, this means that the density of the root is higher near the unit disk. And reciprocally, it means that if the root of the polynomial you consider does not satisfy this property, so let's say that it has half of the roots are within this disk, then the condition number is exponential in the degree. And this actually allows to understand the literature. So some people say that polynomial root finding is a nil condition problem in general. Others say that typical polynomials are well conditioned for the computation of their zero. Actually, what we can see is that indeed for uniform distribution of the coefficients, polynomials are well conditioned. However, for uniform distribution of the roots in the unit disk, the corresponding polynomial is ill conditioned for the problem of root finding. Thank you for your attention.